So the last talk of this session is given by Yamakami sensei.
Sorry. Oh, okay. Well, thank you very much.
The title is too long for me to read.
Well, yeah, that's right. Well, sorry. Okay, so I'm going to discuss about state complexity characterization of the particular things. There are several lines you can actually see. So I just summarized what you are going to expect here. So this talk is all about the LSH, the linear space hypothesis. That's the ideas that I'm going to explain later. And also the state complexity transformation from the restricted two-way non-deterministic finite automata to some restricted version of two-way alternating finite automatas. Through this talk, I'm going to explain about the two characterization of the P subling. I'm going to explain this particular complexity class later on. And also 3D SD-com. So this is the degree 3 directed graph SD connectivity problems. And the final reason I'm going to give the new characterization of this particular hypothesis, LSH, in terms of state complexity. Okay, so first, so I'm going to explain about this particular hypothesis, the linear space hypothesis. So I start with the the background. So I guess that everybody knows about three satisfiability problem is the NP complete. This is given by Steve Cook in a long time ago. And NL, so this is a non-deterministic version of the log space complexity class. So look at two SAT compared to the three SAT. The two SAT problem. So this problem is known to be NL complete problems. Just to give you one example here. So the Boolean formula in the 2CNF form is given. Then now we have to decide whether this particular formula is satisfiable or not. For example, here the 2SAT, 2CNF means each clause has most of the two literals. Okay, so NL is a very robust complexity class. So even if we restrict the 2SAT to something like this one here, when the k is 3, so that each variable, like at the x2, that appears at most 3 times. So that's number k in the form of the literal. So we just simply ignore the negation symbol, right? So this is the 2SAT 3. So in general, 2SAT k is NL complete. Right? Well, at least k is at least 3. Well, when k is 2 or 1, then this problem is actually L in L. So not so interesting. So the nagging one of the the complexity class question is whether 2SAT k is in L or not. Okay. So now we move on to another interesting problem, so-called directed ASCII connectivity problem. So this is the problem of the assuming that the directed graph, something like this one, is given, and also the two particular vertices in S and T are specified. Now your task is to find whether they existed of the direct graph path from S to T. Right? So this problem is known. Is known to be NL complete using the log space minimum reduction. Okay. Now we restrict the same question, the same problem a little bit. For example, so this is the graphs, the given graphs. Now we are actually looking at each individual degree of the vertices. And when k is given here, the k DSD count, when k is 5, right? So if you look at all the degrees, all degrees are actually bounded by k. Well, in this particular case, 5. Right? So in that case, the SD con is well, we defined it in DSD con. So this problem is also NL complete. At least the K, at least then K have to be greater than or equal to 3, right? So we don't know whether this particular question, like the 3 DSD con, belong to L or not. So this is a deterministic version of Logspace class. Earlier, some years ago, the 1998, the Barnes, Bass, and Russo, and Scheiber, they actually presented the very nice algorithm to solve this DSD con with the particular parameters in M and N here, and M vertices and M edges, right? Their algorithm works in time polynomial in n plus n, and also using the space n to the 1 minus c over square root of log n. Okay, so c is just a constant, right? There is the nagging open question is that nagging open question is that here. So that means whether we can improve the space bound. Well, this is actually very close to linear, but not. Well, can we actually reduce this one into n to the epsilon? Epsilon is a constant, but here the exponent is not the constant. It's smaller than 1, right? Because then if the n is growing larger and larger, this is very close to n. Right? Now, so as you see, that the parameter is somewhat important in the practical sense. So what was defined as the size parameter? Size parameter actually give the some information, the size information about the input x, right? Well, in the regular situation, we just simply take the binary size of the input x, right? Now that we will consider the parameterizing the programs. For example, the particular examples and size parameters. For example, then if you're talking about it in a Boolean formula, then well, we might be interested in the number of the different variables or the number of the clauses. Or, well, if you're looking at the graph, well, either directed or undirected, right? We are more interested in the number of the vertices or the number of the edges, right? So those are just a typical example of the size parameters. Okay. Now, why the size parameters are important? Well, we have several different choices. Like, for example, then if you talk about the graph, then we can consider the number of the vertices as the basis to measure the complexity, or we can actually use the number of the edges. But the choice might be not so much appealing to you, but then actually that makes a huge difference. For example, then if you look at the graph like this one here, well, if there's no isolated vertex, then the number of the vertex is bounded by 2 times as the number of the edges. But then the number of the edges is bounded by the square of the number of the vertices. Right? You see this square, so that makes a huge difference. If you just go into the sublinear space. Okay, now, well, we'll define this in parameterized decision problem. So this is just a pair of the standard problem with the size parameter, right? We are going to use the Logspace computable size parameter later on, but here. Well, those situations are actually not new. For example, the Pagliaccio and Peturian's they actually consider the K-SAT and the search version of the K-SAT, the search K-SAT, and they consider the problem parameterized by the number of the variables and the number of the clauses, and they introduce the hypothesis of ETH, the exponential time hypothesis. Well, this hypothesis has been, very popular nowadays. As a basis to introduce or prove the better upper or lower bound of some complexity products. Okay, now we'll consider the multi-tape, the deterministic Turing machine from now on. And we are interested in the machines running in polynomial time and sublinear space. The sublinear means there are these forms. Now we are using the size parameter, right? So m of x to the epsilon. Epsilon is a constant, smaller than 1, and we have some factor, polylog length of binary length x. Right? So this part is not really important as long as the m of x is not that small. Okay, so we just use the word sublinear to mention this particular form. Okay. So now we'll introduce the particular complexity class. This is the class of the parameterized decision problems, or sometimes search problems, right? L comma m. So L is a standard problem, and m is the size parameter, and assuming that in log space computable size parameters. And well, this problem can be solved in time polynomial in binary size x and sublinear space with respect to size parameter n. Right? So this complexity class situated in between L and P, and deterministic complex the CFL, DCFL is just a part of the P sublime, right? Due to Steve Cook. Okay. Now, I just to give you an idea that two set with an n variable and n clauses can be solved in a polynomial time using this amount of space. So this result is just a simple modification of the previous algorithm for the DSP clone, right? So now the question is whether we can reduce this one into this one. And last year, I introduced the practical working hypothesis called LSH, the linear space hypothesis. This is just the linear space version of the exponential time hypothesis. And this says that there is no deterministic algorithm that solves them 2 sub 3, right? Using polynomial time and sublinear space in terms of the number of the variables. So this is just a hypothesis, and nobody has ever proven whether this is true or false, right? And why we take the 2 sub 3 instead of 2 sub? Because then we can't tell whether an LSH for 2 sub 3 is equivalent to an LSH for 2 sub. Because of the square, okay. So, and also similarly, LSH is not equivalent to saying that an LL is completely calculated in polynomial time and sublinear space. So it's kind of the middle between LS is contained in the P sublime and 2 sat is computable in 2 sublime. So this is actually the very funny part here. The P sublime is a very funny complexity class. It's not really closed down in a standard log space reduction. Okay, now we move on to the state complexity characterization. We try to characterize this particular hypothesis in terms of state complexity. So what kinds of state complexity I'm going to discuss? So this is standard state complexity definition, just a number of the inner states, right? And then I'm going to talk about the family of the finite automata. In that particular case, the state complexity of this family is the function, outputting the number of the inner states associated with the index n. Okay. So the family of the finite automata is called an L-uniform. So this is pretty much similar to the circuit complexity, right? So when you talk about P uniform or log time, d log time uniform circuit complexity. So we will use the L uniformity to specify the family of finite state automata. So the family of the finite state automata is called an L uniforms when they exist log space deterministic Turing machine that actually can produce each individual finite automata. Well, actually, it's an encoding of the finite automata. Whenever the 1 to the n is given. Right? And when we say that the two families are actually equivalent, if and only if each individual elements are actually equivalent. Equivalent means the language is exactly the same. Okay, so the state complexity of the transformation is to measure the type 1 machine with an n states can be transformed into another machine, the type 2 machine, with the this amount, T of n states. In that case, we will say the state complexity is T. Okay, so now we have to introduce the slightly unusual notion here, the circular tape. So the circular tape means that whenever the head actually moves off to the right side of the tape, they actually automatically go back to the left side. That means the tape is going like this one here. Okay? And the tape is called sweeping. That means the head actually moves from left to right, always. So a few more things. Okay. So C branching. That means that the well, we are considering the non-deterministic finite automata, so they actually make the non-deterministic choices at every step. But the number of the non-deterministic choices is actually bounded by C. In that case, we will call this machine the C branching. Okay? But then if you think about the family of the 2 NFA, so the constant branching means that we have some constant that bounds every possible element, finite state automata in this family, BAC branching. So that means this is the 2 branching, and this is the 3 branching, because there are 3 choices here, but this is 2. Now, well, from here, so now I'm going to consider the simple 2NFA. The simple 2NFA has the circular tape, and the head always sweeps the tape, and it makes non-deterministic choices only at the right end marker, not the other places. So this is the simple 2NFA. Now, I'm going to introduce the alternating finite state automata. Then alternating finite state automata, they actually have they have existential state and the universal state. In the existential state, well, it's more like the non-deterministic and finite automata, but their inner states are actually partitioned into those 2 states. And roughly speaking, at the existential state, the machine actually takes at least one accepting branches, and if the machine actually enters the universal state, they actually have to have all accepting branches. Right? This is bad because here universal state does not have we'll say the red lines are accepting and the black ones are rejecting. So this particular state does not have all branches to be accepted. Okay, so when the machine actually produces this computation tree, then here, well, this is the accepting subtree. That means whenever you have the existential state, then at least one accepting branch. And whenever you have the universal state here, all branches have to be accepted. So now you actually have this particular accepting subtree. Right? Now here we don't have that accepting subtree. So in this case, the machine rejects the input. In this case, machine accepts an input. Okay. So one more thing, and before it's actually showing the the final results, right? This two-way alternating finite automata is called the f of n narrow. That means now actually I switch from the computation tree to computation graphs. That means when they can possibly produce the same configuration, right? So we are not treating this one as a graph because we are actually not splitting this one into the two different configurations, but so whenever they reach the same one, right? So we just draw like this one. So this is just a graph, not the tree. So the narrowness means that well, we are actually considering this leveled. That means in each level, they have exactly the same state. I mean, here is the universal level. This is the existential level, and so on, right? And we just look at the universal level, right? Count the total number of the different configurations. That is actually bounded by the f of n. Okay. So, okay. So first, I just agree with one thing, right? Every L uniform family of some constant branching simple 2NFA can be converted into L uniform family of an equivalent n to the 1 minus c over square root log n narrow 2AFAs with polynomial blow up of states. But here, so this, well, my question is whether this one can be reduced to n to the epsilon. Epsilon is a constant between 0 and 1, and not including 1. Right? So this is actually an open question. So you see, finally, the state, this is just a part of the segment of the theorem up there. LSH, when LSH fails, if and only if this particular thing holds. I just draw a picture here. For any L uniform family of the simple 2NFAs, right? Using these states and constant branching, this can be converted into L uniform family of the 2AFA using a polynomial amount of the states compared to this one, right? And n to the epsilon narrow. So if you can make this transformation, then that is equivalent to saying that the LSH is wrong, or the other way around, right? So this is just if and only if characterization. Now, so this is just the last slide. Now we can think about the non-uniform version of that statement. What that means, non-uniform LSH, linear space hypothesis, means that the 2SAT3 and this using the size parameter, the number of the variables, does not belong to the P subline slash poly. Yeah, this is similar to the P slash poly. Using the machine is supplied with the polynomial size twice string for each input length n. So non-uniform LSH fails if and only if for any constant, there exists a constant epsilon that satisfies the following things. Every C branching simple n state 2NFA. Well, we don't need to worry about it in L uniform now. So this particular 2NFA can be converted into the equivalent n to the epsilon narrow AFA of polynomial states. So this is the exact statement for the non-uniform LSH being failed. Okay, well, thank you very much, and I'm really happy to ask a question.
text that saying, for instance,
So
field of time uniformity or something else?
you're talking about this one, right?
Yeah.
Okay. Could be. Yes, but I haven't thought about it.
Okay.
Do you have any suggestion?
No. You know, if you do uniformity first base and you reduce the uniformity. Yeah, so I don't know whether this will work out.
Oh, well, first thing I thought about the L uniformity because the whole question is somewhat between L and ML, right? So the log space computation. So it might be easier for me to use the log space restriction instead of just P uniform or the other uniformity.
The keys just drop.
Yeah, that's right. Oh, going down.
Yeah. Field of time uniformity, for instance.
Oh, I see. Yeah, that's right. Could be, it could be I can replace this uniformity with a much weaker uniformity, as you said. Well, that will be a future discussion, I guess.
And just another question is
Sure.
P-sub-lin complexity class.
Next
I
one.
think it was called P-sub. P-sub. You know this complexity class?
Oh, I see. Oh, you're talking about this
yeah,
one, right?
P-sub-lin, yeah. So this is not closed under Logspace reduction?
Probably not.
Probably not.
Because, this complex class is in between an L and P, so that in the case that the P equals L.
Okay, but there are tons of different other complexity classes between Logspace and polynomial.
Yeah, that's right. That's right. You're right.
Yeah.
So I haven't really thought about in that direction yet. So comparing a whole bunch of different complexity classes, which includes which kind of thing. Not yet.
Any other questions, comments? All right, so let's send the speaker again.
Okay. Thank you very much.
And I wish I could say to Joseph, please restart the discussion, but now we have a speaker, so I'm so sorry.
Okay, hi. I'm staying in Halifax. Well, I attended a conference, international conference. The conference is already over, and well, I gave a public talk, and well, the talk itself seemed to be okay to me. Well, then I discussed the state complexity of the using state complexity to characterize the linear space or sublinear space hypothesis, LSH. I tried to kind of improve the characterization in terms of well, different model or different uniformity, well, in the future. Okay, so meanwhile, so after the conference, I took a liberty of just going sightseeing for a while. So Halifax itself is not a big city. It's facing the Atlantic Sea. The place is very famous for the sinking of the Titanic, because there's the victims. Some victims of the Titanic are actually buried here. I didn't go to the cemetery in this trip. Today I visited the so-called the Citadel. It's the military fortress, and that was a very interesting place. It's kind of very hilly, and so you have to really go up a little bit the hill, and then you actually get into the fortified surrounding. And then you will see the several the interesting events. They actually prepared the several events somehow, some activities going on. The people wear the old-fashioned clothes and the military uniform, and they try to present or they actually show that what really happened in the long time ago, and also they actually give an exhibition of the war times, like the World War I and II, and also the Korean War, right? And they also show us several pictures of the what really went in the time of the war, right? From the point of the Canadian soldiers, because then there's a lot of Canadians actually, they died during the war, to liberate the occupied citizens. Okay, so that's the things, and like, well, unfortunately, the first couple of days, weather wasn't so nice. We had an occasional rain or drizzling, sometimes, particularly, when we went on the excursion. Well, we went to the World Heritage site, but on the way to that site, well, we went to the harbor town, the town with some harbor and the shipyard kind of thing, and that was a very interesting city. But unfortunately we had rain, and after the trip, the conference organizers, they chartered the bus, and then the bus brought all the participants to the conference, to the World Heritage Site, and brought them back to Halifax. We went to the French restaurant, and toward the close to the end of the banquet, we had the heavy rain, and we are actually caught up in the the spat of the rains, and we some of us are forced to stay in the restaurant for a while until the rains sort of stopped. So I took the walk back to the this residence with a couple of people. Okay, so hope to see you sometime. Goodbye.